Hey, hi, in this video I'll do a short overview of Lisp and follow it up with a demo of Lisp mobility. Lisp or location ID separation protocol is a routing architecture which separates the endpoint identity from its location. Traditional IP routing architectures have a single namespace where an IP address identifies both the location and the identity of the endpoint. Lisp is basically an overlay routing protocol over a traditional underlay. Lisp is very analogous to a DNS system, that is, when the router doesn't know where the destination is, it sends out a query to a map system, which then provides it with the location of the endpoint. This improves scalability, as the router doesn't need to hold a huge routing table. Lisp has three major components: the ingress and the egress tunnel routers, which are the edge routers responsible for encapsulating and decapsulating the Lisp packets. Now, both the functions can be merged into a single router, and when it is done, it is called an XTR router. The map server and the map resolve is the one which maintains the endpoint database, and the XTRs use this mapping system to query the endpoints that they aren't aware of. In addition to XTR, there is also a proxy XTR, which is a router which enables communication between Lisp and non-Lisp site. With that brief overview, let's quickly jump onto the demo. Attached is the topology we'll use for our demo. We have 5 sites represented by border routers R1 to R5. Sites 1 to 4 belong to Lisp domain, while site 5 is a non-Lisp site. That is, it doesn't run Lisp at all. Each site also has the addressing mentioned. Router 20 emulates the service product cloud. Router R6 is the mapping database, that is the map server and the map resolver. Each site also has a router like R7, R8 and R9, etc., which simulates the end host within the sites. The solid lines from these routers indicate the primary exit point. You will also see dotted lines connecting from these routers to other sites, like R7 has a dotted line to R2, R9 has a dotted line to R4. These links are connected in the demo topology but are in a shutdown state. They will be used for demonstrating Lisp mobility. That is, if I want to show the host movement, that is R7 from R1, which is in site 1, to R2, which is in site 2, we will just shut down the primary link, that is the solid line, and unshut the undotted links. This will emulate our host movement from one site to another. We will do similar movements of R9 between site 3 and site 2 and site 4. To save time, I have pre-configured the underlay routers, that is R1 to R6, and I'll be focusing only on the Lisp configuration in this demo. The underlay is actually running a routing protocol to provide reachability between the router interfaces and the loopbacks. ISIs is actually used as a routing protocol in this topology. So let's go ahead and quickly check the configs on these routers. Okay, so let me log into router 1. Sorry, it's just taking too much time. Let's do a show IP in brief. And you can see that these are the interface IP address that is towards the cloud, and this is the internal interface IP address and the loopback IP addresses. Now if I check the routing table, you'll find that I'm able to reach the loopbacks of all the other routers. So .2, .3, .4, .5 are loopback addresses for the routers R2, R3, R4 and R5 respectively. But if you notice that I don't have any knowledge about the site subnets like 172.16.120.0 and 130.0. So similarly, the 100.0, which is the site subnet, which is the internal subnet on R1, will not be available on R2. So let's go ahead and quickly check that. And you can see that I don't have 172.16.100.0 under the routing table of R2 at all. So with that, let's begin configuring Lisp. Let's configure first our map server, which is our R6 router. So this is my R6 router, which will be used as the map server. So Lisp configuration begins with, it's pretty easy, and it begins with router Lisp command. And then you mention what's the site that you want. So we have to define sites with authentication keys and the prefix that will be reachable through that site. We can create separate sites for each of the prefix, but in this demo I'm going to group them all into one site called campus. So let's create that site campus. I will use the authentication of Cisco. and I will say I can accept the following EID prefix. I'll do authentication key Cisco. I'll do an EID prefix 172.16.100.0/24, and I'm going to add accept more prefixes to this command. This ensures we register /32 hosts in the database. This is required as one of the few hosts can move between the sites, and we don't want the entire subnet to be moved across between the sites, and this is required only in case of Lisp mobility. Okay, so similarly I'm going to add the other subnets, and then /30 /40. I'm going to also need to mention that this router needs to act as a map server and map resolver. So I'll do an IPv4 I need to exit out of it, sorry. IPv4 map server. IPv4 map resolver. That's it, and that's the configuration that's done for R6, that is the map server. Let's quickly check what's the site status. So we do that with list site, and you can see that I have the following prefixes defined on the map server. But if you see that none of them are up, because none of the sites or the routers or the XDR routers have registered those prefixes. With that, let's go ahead and quickly configure our site routers. Those are the border routers. So let's configure R1. Most of the configurations between all the routers are similar. So I'm going to do a router configuration for R1, and then we will do a similar configuration on all the other routers. Configure our R1 router. So we begin with router Lisp. Then we define a locator set. Locator set are generally used if there are multiple ATR routers within a site, and we group the border routers or the ETR or the XDR routers into one locator set. So we're going to define a locator set and call it site1. This can also be used for redundancy purposes if you have two routers, right? And then we're going to assign our IPv4 interface, which is the loopback 0 interface, as our routing locator for that site. And I'm going to assign a priority of 10 and a weight of 10. Now the usage of priority and weight is again useful when you have multiple routers. You can actually change the priority and weight and influence the incoming routing towards the site. Once you do that, now you have to go and define your EID space that will be available from this site. Now since we are using Lisp mobility, we're going to define the EID space as dynamic EID. The other way is to basically define a static EID when you know that there is no mobility going to happen. But since it's a mobility demo, we have to define the EID space as dynamic EID. So we're going to define a dynamic EID space, and I'm going to name them. This is just a name, so I'm just going to use that as 100.0, and I'm going to do a database mapping of that prefix. Then map it to the locator set that we defined. So that's it. So similarly, we have to define it for the other dynamic EIDs that could be available within the sites. So since I said that there is a Lisp mobility and each of the subnets can be available on all the sites, so we're just gonna go ahead and configure the other dynamic EIDs as well. So let's do that. So let's configure 120.0. This will again be 120.0. Similarly do for 130. And we again do 130. And we can also do for 140. So all the mappings has to be created if all of your subnets are going to move around all the sites. Once this is done, we need to tell this router to act as an XDR router. That means we need to define it as both an ITR as an ETR, and we do that with the following commands: IPv4 ITR and IPv4 ETR. And once you do that, you'll immediately find that the Lisp interface comes up in the router. We also need to tell this router what is our map server and resolver. So we use the IPvTR and use a map resolver of 1.0.6. And similarly, ETR map server, which is again 1.0.6, but this time we pass a key variable of Cisco, which was the same which we configured on our mapping system. We can also use a PXDR, which would be used by this XDR to route traffic towards non-Lisp site. Although we are not going to demonstrate PXDR in this demo, let's just go ahead and configure the PXDR as well. Use PTR and 1.0.5. So for any non-Lisp prefixes, the router will actually tunnel the traffic towards the PTR, which is the 0.5. And that's it. That's the configuration that needs to happen from a Lisp perspective. Now, one of the other things that we need to do is configure Lisp mobility under the interface. So let's go ahead and define that 0/1. We do a Lisp mobility, and then we define the dynamic EID name that we had actually given, which is 0. This means that the interface is actually enabled for Lisp mobility. And that's it. That's the configuration that will be there on the router 1. A similar configuration exists on router 2, router 3, and router 4. So I've already configured, actually used the configuration in a notepad. I'm just going to paste these configurations to save some time. So if you can see the XTR2, it's basically defining another locator set. I'm just naming this as site 2. It's again using the loopback 0. And again, I'm defining the EIDs. I'm defining 120, 100, and 130. I'm not defining 140, but I could define. Again, as I said, it depends upon which subnets will move around within your sites. And I'm again then ensuring that the router acts as XTR by configuring both the ITR and ETR maps, and then I'm configuring the Lisp mobility under the interfaces. So similar configurations will be there for XTR3 and XTR4. So I'm just going to use this configurations and paste them to save some time. Let's go ahead and do that. So let's go ahead and do on router 2. Just go and paste this configuration. No errors. And as you can see, immediately the Lisp interface comes up. Similarly, now we'll go to our router 3. And we paste the configs. So we don't see any errors as such. Good, and the Lisp interface comes up. So let's do again for router 4. And we go to router 4. And paste. So no errors, and everything seems to be up. The Lisp interface has come up. So since we have configured all these routers, let's go back and to our mapping system. We'll just see what's the change. There's no change because most of our EID mappings are dynamic. So once it finds out a host mapping, then it will update the mapping database. Now let's go back to our diagram and see that now we had hosts, R7, R8, and R9 were actually simulated as hosts. So what we'll first do is basically go and configure R7. It's already configured with an IP, and then we'll use the R7 IP to see how it connects back to other site addresses. So I'm gonna use the interface, which is the solid line interface, which is the primary interface now. So let's go ahead and log into our R7 router. Let's do show MP interface brief. As you can see, it has one interface which is configured with 100.100, and all of the interfaces are shut down. It just has a loopback interface of which we are not going to use. And if you do a show CDP neighbor, all I see is router 1. So because the 0/1, which is connected to router 2 to simulate our host moment, has now been shut down. So let's go ahead and just check if we can able to ping the gateway. 100.1. and I will ping. Similarly, go to our R8 host. If you go back here, R8 is connected to site 2. So go back to R8 and do a show IP brief. It has one interface. If you do a show CDP neighbor, this is actually connected to R2. So let's try to ping 116.120.1. This also pings. So let's now try to ping between the hosts. So let's go to back to our R7 and then ping 172.16.120.100, which is our R8 host. So as you can see, after a couple of drops, the router successfully pings the other end host. The first two drops were basically attributed to the map request and map reply that the Lisp is actually using to get the location of where that prefix is located. Now, one of the interesting things to see is since R7 is connected to R1, this is R1, let's go ahead and check what's the routing table on R1 with respect to 120.0. So do a show IP route 172.16.120.0, and you find that there's no subnet available on the routing table, but still we are able to reach the subnet, and that's what the Lisp encapsulation is doing. So let's go back. Let's go to our mapping server and check this. Now, as you can see, now you have two new entries. One is 176.16.100. Remember the /32? This is basically because of the accept more prefixes that we actually used, and it's being registered by 1.0.0.1, which was our R1, and the second address is registered by R2, which is 1.0.0.2. Now, similarly, if you go back to R1, and since the subnet is not available, how was R1 able to route the traffic? So let's do a show IP ceph table for 116.120.100/32, and let's do a detail on this. And as you can see, when you do a ceph detail, you'll find that it's actually doing a Lisp encapsulation for that particular subnet. Now, similarly, let's see if we are able to ping all our other hosts, which is 130.100. Okay, so we'll have to check what's the issue with 130. Okay, shows CDP neighbor shows R3. You go to R3. Between 116, 131. It successfully pings. You can check our mapping database. You can see R3. Let's try a ping again. And it successfully is able to ping now. I just took some more time to populate its map cache. So if you look at even R1, so you can now see Lisp map cache. It can find that it has already found 120.100, and this is the routing locator because the mapping system has sent those information out. And similarly 130.100, it has found. And similarly, if you look at R2, show IP Lisp map cache, you will find that it has ID for 100.100. Since it never had a communication with 130, it doesn't have that. And similarly, if you go back to R3, map cache, you'll find that it also has an entry for 100.100/32. So that enables ping across all the routers. So let's go ahead and do our mobility demo. So now let's go back to our diagram, and you can see the R7 was connected to R1. So what I'm going to do is I'm going to use this dotted link, which is already there in the topology. I'm going to unshut this link. I'm going to enable this link, and I'm going to configure this router's IP address interface with this IP address, which is the gateway of this R7, and then see how it works. Okay, so let's go back to R7. Okay, let's do show IP int brief. Okay, so it's connected to 0/0. So what we do is interface Ethernet 0/0. We do no IP address and no shut. Sorry, we just shut this interface. Interface Ethernet 0/1 and configure 172.16.100.100. This is just to simulate hosts. In a real world scenario, you don't need to do this. We'll do a no shut. Okay, so let's see if R2 already has the interface IP addresses. Yes, I have configured the Ethernet 2 already with 100.1. I'll just unshut the interface. Ethernet 0/2 no shut, and so I'll just do it for Ethernet 0/3 and no shut. And let's go to our R7. Let's do a show CDP neighbor. And as you can see, earlier it was R1, now it's R2. Now it's connected to R2. So now what we can do is we'll just try to ping our 130.100 again. And see, as you can see that after 2 drops, again I'm able to ping, and those was because the host has now moved from site A to site B, or site 1 to site 2, and it took some time for the cache to build up. And if you go to our mapping system now, you can see the earlier mapping system was 100.100/32 was available from 1.0.0.1, which was site 1. So let's see it now, and you can see that this has immediately changed, and this change happened about 33 seconds before. So 100.100 has changed from 1 to the site 2. Similarly, we can actually do it for our router 9. So let's go back to this thing. So R9 was connected to R3, so let's move it to R4. So let's go to R9. This was our 130.100, so let's do a show IP int brief. Okay, and unshut the interface, so interface 0/2. I'll do a no shut. Interface Ethernet 0/0. I will do no IP address, shut, interface Ethernet 0/2, IP address 130.100. And just do a show CDP neighbor to just see if it's correctly going across to the other router. And this is connecting to R4, so we need to check this. So R4 interface Ethernet 0/2 is no shut. It's now connected to R4. So let's ping from our host 1 again to 130.100 and see what happens. Let's do pings. So let's just do a ping to our gateway first and see if it's able to ping the gateway. It's able to. Let's just show interface Ethernet 0/2. Let's do our map cache. Let's just check if it's changed. Yeah, 130.100 has gone to 0/4. I think it should be able to ping. It pings. It just takes a little bit of time, but it pings. So thus, you can see that with Lisp mobility, when a host moves, the routing locators register the updated information to the map server, and the other routers are able to use this information to reach the host. The updated cache, as we can see here, is basically a /32, which means the location moves only for that particular host. Other hosts within the subnet will still remain connected to the existing site, which could be site 1 or site 3 in this case. So as you can see, this is a very powerful feature uh, provided by Lisp, which when applied to a campus network can address the host mobility issues between switches without having to configure trunks all over the place in the campus. We can have campus edge switches running Lisp and update end host information to a database, and with Lisp mobility address their movements within the campus as well. This can actually, this is an exact concept which is used in the DNA secure access fabric architecture, where all the edge switches run Lisp in the control plane and uses routing completely in the underlay, thereby completely eliminating the spanning tree and its associated labels in the campus. Though DNA also uses VXLAN from a data plane perspective and ties with trust sector segmentation. From this demo, you can actually get the premise on how it uses Lisp mobility at its core for its functioning. So that's all I had for this demo. I hope it was useful, and thanks for watching.